of time, possibly if you're working from home, to be involved in these webinars, some good training for when things do turn back to normal, and again, to hopefully get ahead of your market the best as possible. So I also realize this is probably your 20th webinar this week, but I don't discount that. I hope you still learned something today, and I hope we have fun doing it. So today's agenda, I'll do a quick introduction, and we're going to talk about complex lasers making life simpler. That's going to be in conjunction with adaptive welding and inspection. And then with those lasers and with a lot of other equipment, what to do with all that data. So with that data, OEMs are looking for traceability, and also how can you better make your line efficient. We're also going to dip a little bit into artificial intelligence and machine learning with that data. And lastly, we're going to talk about how do I weld that. So we're going to touch on some advanced materials that we're starting to see in the marketplace, and then some methods to join those materials. But first, again, my name is Josh Leith. I'm a product manager for the welding robotics at Yaskawa. I've been with Yaskawa for about 3 years, and I've been in the product manager realm for well over a decade. That's how we tailor our product lines as we go forward. So we'll have time at the end of the presentation for some questions. So some quick housekeeping. If you have any questions, please enter it in the chat. We'll review those at the end. We do have a lot of high-level information to cover here in about 30 slides. So I will be moving pretty quickly. So if you have further in-depth questions, if we can't cover them today, still submit them. We will follow up after this webinar. So first, complex lasers making life simpler. So these are lasers not necessarily for welding, we'll get to those here shortly, but for sensing. And why would I want a laser for sensing? Well, primarily they're fast and they're incredibly precise, down to a fraction of a micron of repeatability and defect detection. In fact, I believe it was my Keyence account manager told me that Lego uses their sensors because Lego blocks, the simple plastic blocks, have a tolerance of 1 micron, which is why they're so consistent in fitting together. So across industries, be it automotive, be it doing PC boards, doing toys, everybody's using a variety of lasers for quality inspection. With automotive, it does give you the traceability that you need for weld seam inspection. So if they have a certain grade of porosity that they're looking for, you can measure that, you can track that, you can store that as data, and give them the traceability they need from part to part. Also with these lasers, they're fine enough, again, down to a fraction of a micron, that if there's raised print on a part, such as a serial number, it can read that and store that information as well. It's also faster to find your workpiece than wire touch. With wire touch, you're actually bringing the robot arm down to the workpiece to find out where in space that workpiece is. So it can actually adapt your weld program for that. It can also be used for verifying or measuring assemblies. So you can see at the bottom here, the image showing the PC board. If there's a part that's missing on that, or if I have a box that's going down a line that's missing pieces inside the box, I can actually measure that with a laser to determine if a part is there or not. This is also ideal for just about any arc type welding or laser welding when you're trying to find the seams, track the seams, and measure those seams for quality. So on these laser sensors, just looking at what you're looking at on specifications, again, I mentioned that they're down to less than a micron of repeatability. It's the same laser that's used for inspection and measurement as it is even for weld line verification. Typically, it's going to be red, green, or blue lasers. The blue and the green are more relatively new to the market, and they aren't affected by the weld pool heat reflectivity. So that infrared heat that's in that weld pool used to be very hard to track with a red laser without a lot of fine tuning. We can get around that now with blue and green. They work by triangulation for figuring out what angle it's reflecting that laser back into the sensor at to determine what it is that it's measuring and finding. You do have a Z and X axis max range, typically from 20 to about a meter in height, as wide as half a meter in width. So you can do to very small parts to very wide ranges of parts with these. So here's a case study with laser inspection to give you an example. This was working with BWI, who's a strut manufacturer, shock manufacturer, and they chose a Vitronic brand laser. Now these lasers are mounted on the robot arm with the torch and the rest of the ARC equipment. They grade each of these welds with these lasers after the weld is complete, but before the weld's even done, it verifies that the part's in place and it's actually that it's the correct part. If it's not the correct part, it'll sound an alert, of course, give you a red light to show a no-go situation. But then after the scan, they get a grade. You can kind of see the HMI presented here in the middle of the screen, and it gives them a grade on each of those welds. And they're looking for the profile, the length, the undercut, porosity of the weld, if there's any whiskers, cracks, and if there's excessive spatter. So that data is then stored for that weld, for that part. If the part is actually bad and it determines it does not meet those conditions, the weld torch actually comes back and blows a hole in the part. So that part is deemed useless, and then it tracks that the user, the operator, actually removes the part and then places it in a discard bin. So we have a video of that on this next slide here. Get these queued up. And it'll start playing in just a moment. And so again, we see the part in place. And this is on a small positioner inside the cell. We'll see the robot come down. The door of the laser opens briefly, checks the part, which was very quick, kind of hard to see in that video angle. The weld's made. Laser again comes down, inspects the weld on each of the robot arms. And because this was in teach mode here, the positioner is running at a reduced rate for safety reasons. And then two-sided tooling actually comes back down inside the tooling. You saw briefly there a red beam before the arc started to verify the placement of the part. And then the arc, of course, starts to weld the part. And then we just had the second scan there on the other side. So at that point, the HMI would deem that those parts are good or bad. And in a moment here, we'll see how those shutter doors work in this situation, because those sensors do need to be protected from that weld spatter, especially if it's in a heavy welding environment. These are smaller parts, so again, just being more cautious when it comes to utilizing those shutters to protect the laser. Actually got another weld here. Here you can see that shutter and see what that beam looks like. So again, very quick process overall. To get back to our slides. So again, checks for part position, it welds, inspects the welds, and provides that pass-fail response. Also, you can use for part inspection, so not just welds, but our parts in the correct place in an assembly. So if I have different studs, for example, that come through, or screws that need to be present on this weld, I can track each model to determine yes or no, are those parts in place, and is this good enough? That's one of the tricks in this, though, is with any inspection, what is actually good enough? So if I'm doing manual welding with a semi-automatic gun and I see my weld, I can kind of judge, because I'm a trained welder, if this is a good weld or a bad weld. And is my undercut right? Does the porosity look right? With the computer's measuring everything. Again, because of that laser is so precise, how good is good enough, or how bad is bad enough that I want to reject that part. So that's where some of the artificial intelligence comes into place to help the user decide, but also under OEM influence. I think we'll see more parameters coming from those OEM automotive manufacturers in the near future to help us determine, again, what is good enough. So with those lasers too, we can do what we call adaptive welding. So that could be as simple, again, as that wire touch sensing, to a little bit faster with a pinpoint touch on the laser, more simplified laser. We can use camera systems, or we can use, again, like what we saw with that laser sensor before. And that is to find the seam in place to make sure I'm starting in the right correct position. And then I use a relative job function to actually shift the entire job point to be in space where I need to be to complete that weld job. On the other side of that, though, more, again, what we call adaptive welding, I can do two different pieces here. I can use that laser, again, what we call on this slide the Moto ILT, to actually track if that seam is changing while I weld. So if I have any heat deformation, for example, while I'm welding, the relative job and the shift will actually affect that weave and that jog of the robot as it's welding. I can do the same thing also through ComArc, which is through the arc seam tracking. So I'm actually measuring the gain and drops in voltage and current to make sure that I'm staying tight inside that weld seam. So we have all that data from the lasers. I have scans of the welds to make sure that they're good or bad. I have information coming out of the robot controller and other equipment. What can I do with all that data? So you're probably familiar with the Industrial Internet of Things, or Industry 4.0. This is kind of bringing together all the factory automation that we've worked on for a couple decades into more of a smarter space. All of that equipment, again, is creating data. It's giving me process times, it's giving me part counts, I'm looking at weld parameters, I can see consumption rates of consumables. So I kind of break that into 4 sections here, as you can see in this graphic. If I look on the right, efficiency. So are my machines running efficiently? Are they doing what I think they're going to do in a day when it comes to cycle times and part production? I can also look at uptime. So it could be an efficient machine, but if it's constantly having to stop for some reason or another, be it maintenance or operator error, again, I'm losing money on any of that downtime. So I can prevent that downtime and ensure uptime with that data. I can also measure quality. So again, if I'm scanning parts and determining if they're good or bad, I can give myself a quality assurance on those parts. I also provide visualization through this data. So just as you're used to seeing charts and graphs of performance, I can visualize that data from my machines in different charts and graphs to achieve different KPI targets. To give you an idea what that would look like, Yaskawa's product for this is called Cockpit. There's lots of different industrial products though out there. They all kind of work the same though. One of the major differences is going to be if that data lives locally or if it's always sent to the cloud. In the case of Yaskawa Cockpit, it is locally stored and then sent to the cloud as needed. So in this case, we have an assembly line. You can see the controllers, the robots, servo motors, AC drives all being used. All that's creating data. All that data goes to Yaskawa Cockpit. At Cockpit, it collects that data on a server, and then I can, at this point, either execute on that data or send that to the cloud for further application. So execution at that point might be defect monitoring or a preventative maintenance, for example. So if I know a servo motors run so many hours and it's going to need lubrication at some point, I can have planned downtime for that lubrication. With that data, then I can do the analysis and monitoring locally or send it to the cloud. With the cloud, I can implement something like IBM Watson or other analytics to determine is something up to par that it needs to be. If it's not, what tweaks can be made based on the data that it's seen in the past. So if it noticed that a parameter changed versus cycle time change, how do those influence one another, and how do I make changes to my production to increase production overall? That also can come into play with machine learning, which you've probably also known as artificial intelligence. So if I have a scan of a part and I have that data, I can send it to the cloud. If I have an algorithm and artificial intelligence in place that determines how to weld that part based on the shape, the size of the seams, whatnot, it can also then generate a program, perhaps, and then send that back down to the robot to execute that. So you kind of see that here from feedback down to data center, in some cases, back down to either PLC or directly to that controller to execute that feedback that's been provided. So lots going on with the data, but kind of endless opportunities with it. Again, looking at Yaskawa Cockpit, what that looks like on a local simplified level for visualizing your operations. Here we have an example of what we call our TAT lab. So this is our demo lab if customers come in to check out their parts or some solutions that we've made for them. And here's a variety of robots that currently live in that TAT lab. So I can see in the vision lab versus the welding bay, what controllers are being used, what model robots are being used, what the status of that robot is, operating rate, so on and so forth. So at a glance, I can see the status of that robot. Again, our server lives locally. So in this case, it's going to be in that TAT lab or at least somewhere on our premise. I can have multiple of those servers. I can connect those to a mail server if I don't want that information out of the factory, for example. Our majority of our customers don't want that information actually going to the cloud. They want to keep it locally just for security reasons. But I could connect that to a mail server. So if I want alerts to go out, but not any other data, that mail server is going to give me an alert on my phone saying there's an alarm on a certain robot, or maybe there's a cell that's not meeting specific targets. This is all going to be controlled by that mail server. One of the benefits of this is asset management. So again, is that robot doing what I expect it to be doing? Is it idle a certain amount of time a day? Is it actually operating a certain amount of the time a day? I can also see what my production volume is, operating rate percentages. I can also get into maintenance analysis with that, as far as, again, am I seeing too much torque on a reducer that I know that's about to fail in time? So I've had this robot for 12 years. Do I just go ahead and disassemble it and replace all the parts, or do I wait till failure? So this is going to give me an idea of when those failures are going to occur. This could also be on consumables. So on a welding robot, I have weld wire and I have gas. I can actually track how much weld wire I'm using, or if I know I have so many pounds or so many feet in a barrel, I can count that down. So I have an alarm that could go off to warn me your consumables are about to run out. Same thing possibly for paint, for adhesive, for anything that I'm going to run out of that's going to cause downtime. So again, prevent that downtime from occurring. I could also add vibration and temperature sensors to this. So again, if I'm seeing excessive vibration in a positioner, again, that might tell me that something's going wrong, again, so I can prevent that downtime by having it more planned in that sense. So a lot of issues that can be cured before they ever happen from that maintenance analysis. I also have alarm notification with Yaskawa Cockpit. So just as you get an alarm on the robot pendant, that's going to pop up in Cockpit. I can have that notify an individual to say something's wrong, but also I can look at those alarms and that alarm history. If it's a reoccurring alarm that's continuing to cause that robot to not meet its targets, I can see what's causing that. It does give me details, timestamps. I can even do logins as well to kind of control as far as what alarms are going off when who's using the robot, for example, so I can maybe get some more information from that person on what they know of what's going on. Popular aspect from Cockpit, also available with other similar services from other companies too, are backups. So I have all this data that's stored locally in the controller. I have the data that's stored in the server. I have all my jobs that are constantly being tweaked possibly by the operators. If I want to back that up and from time to time to make sure that, like other services, we have different add-on functions. So for example, we already have pre-built ARC monitors, oscilloscopes. It is OPC UA, perhaps a Miller power supply or a Fronius power supply, feeding that data into the robot controller and feeding it into Cockpit. So here's an example. We take this cell to trade shows typically. It's our beer serving robot, so obviously very popular for trade shows. In this situation, it was serving two different types of beer. It had Blue Moon and Sierra Nevada, it looked like, and I could see, as far as what each guest chose, how that depleted the kegs of beer. So in this case, it looked like Sierra Nevada was either more popular or Blue Moon just got replaced there. So I can see again, popularity of each. I can see the analytics of how many beers per hour I'm serving. I can also see when that keg's about to go empty because, again, planned downtime, I can replace that keg before we're out of beer in that sense. So one kind of fun application for that, but gives you an idea of what that visualization looks like. Here's another demo that we had at the trade shows. This was from our Drives in Motion side of the company. And this was a 3D printer. So from that 3D printer, I'm getting data from the extruder, what the temperature of that extruder is, if it peaks, what the average is. If I know something's going possibly wrong with the 3D print, I can look at that temperature to say if maybe it's too hot or too cold, and I can tweak that to make sure that the print quality is better. I can also see my consumables here with how much filament's remaining. So I know, again, planned downtime, I need to replace that filament in the next so many feet or so much prints to make sure that I don't have an error or scrapped part down the line. I mentioned as far as the support for OPC UA, so other devices that do support OPC UA, the cockpit acts as a server, and you can retrieve that data and utilize that data through any type of custom web API that you might want to do for that. So with that data, I mentioned before machine learning and deep learning. Artificial intelligence is kind of the coverall term for that. So basically, I'm getting that data, I'm preparing that data, I'm training a model. So I might have a model that's trained with many failures, for example, of how to pick up a round apple versus a long banana by the same set of grippers. That's all done through simulation. It tests that data, and then it improves that simulation output after each run. So that's kind of the gist of machine learning. We use this with IBM Watson. We can actually use this for grading weld seams, which we'll see in a moment. So just based on the sound of the weld seam and what we know a good weld seam sounds like and a bad weld seam might sound like, does it meet that profile, that sound signature of the good weld seam? I could also, again, scan a part with one of those lasers, determine where my seams are at, based on those models and simulations that it's already run, what's going to be my best approach for welding that part. So here's that IBM artificial intelligence using sound waves. So this was a demo that we had at IREX in Japan last year. We'll be showing it in our trade show demo at IMTS and FabTech this year, assuming those shows still go on. But again, weld makes a sound. If you ask any trained welder, does that sound like a good weld or a bad weld? Generally, they're going to know yes. They had a lot of popping, maybe a lot of spatter, a lot of porosity on your weld, or no, that sounded pretty good. So we're going to see a quick demo of this. And this demo is in Japanese, so I'll try to not translate, but maybe narrate here of what's going on. So this is being based through our Yaskawa cockpit, and they're going to actually create a gap in the weld here to determine, again, the different sound quality that's going on. So the first robot's going to do the good weld, and that's going to be the weld fully in joint. And you can see on the screen as it's measuring that sound signature, it's going to start grading those lengths of weld. So again, simply based on that sound signature, no lasers, it's determining that's a good weld. The second robot, everything's been shifted a little bit. I think it was like a 10mm shift. So it's not fully in joint. So that sound signature is going to sound different if it's not fully in the correct weld joint here. And you'll see those fails start to come across the screen. Now, in a real life environment, you might mix that also with a laser, and that laser will be able to measure the porosity, whatnot, to say, okay, it sounded like a good weld, but was it really a good weld? What other parameter can I use without doing a destructive test?
また、安川コックピットの追加機能として、品質異常を簡単に確認できる
So again, all that information goes to Yaskawa cockpit, and with cockpit, I can store that. So if I have to show traceability for a OEM manufacturer, I'll be able to have that traceability available to show them here was one factor that we used to show that this was a good weld versus a bad weld. So going one step further, again, I mentioned if I had a part, and this is kind of the creme de la creme when it comes to robotic welding. How can I just throw a random part at a robot and it knows how to weld it? So this, again, would utilize offline programming software such as a simulation software. It's going to scan the part and generate a point cloud, and then it's going to set the correct parameters that it's determining based on the material being used, the thickness of the material, what type of weld it is. And we have a partner that does this called Path Robotics. So they're still in a lot of R&D phases, but they do have a few pieces of equipment out in the field. And we have a video to show you how that works as well. So this customer is doing exhaust systems, I believe. Yes, the muffler systems. So you kind of read along, but basically this positioner is adjustable in width, so easily adjust any width of these muffler exhaust systems. You can see different sizes, all about the same idea though. I have a tube coming into a plate, and that's what the laser is going to be looking for. And I also have the outside cavity that's been tack welded, thin gauge steel. What do I need to do to be able to follow that seam all the way around, especially on these oblong pieces that you see here? So it does have to be in a dark environment for this system in the cell. So you see the lights go out, it does its scan, it rotates that part, it finds those seams. They are using a red and green colored laser system. I mentioned before that green is good for reflectivity as well as if there's a hot spot on it. So you see it generates the model. And then their software is detecting where those seams are at in those models. And you can kind of see in purple, it's highlighted there. So in this case, the user has a chance to verify, is this correct or not correct? So simple MIG setup. Torch comes in, positioner does its part. That's a Yaskawa positioner and robot, so you have coordinated motion between the two using the same robot controller. So your repeatability is going to be perfect every time. So that was the inside, which a little simpler because it's always going to be a round, again, tube to plate. But here we're going on the outside for this shell, and that's an oblong shell, but it's still able to weld that part. So that's one application of AI welding. I've seen other similar systems, many using our robots, but same idea. I'm scanning a part, generating a point cloud, and then through some secret sauce on my software, able to generate what that weld's like. So last portion of our webinar today is how do I weld that? So trends of materials, we're seeing, especially in the automotive market where a majority of robots are used, second and third gen steel's being used, new aluminum's being used, but the whole idea is either lightweighting or stronger materials. So with lightweighting is going to come thin stamped parts out of steel or aluminum. We're seeing a lot of different aluminum alloys being used. And then again, those next gen advanced steels. Also, we're seeing more and more dissimilar metals, such as engine cradles and battery trays. And we're required to meet higher safety ratings. Along with that, of course, the customer wants something that looks nice. So higher aesthetics as well, if it's any exposed welds. So looking at aluminum and thin metal, more and more that's being done more simplified, I guess you could say, by the power supply. So I'm not adding additional equipment necessarily or any new methods. I'm still using a robot with a MIG torch on it, and I am able to achieve, in this case, TIG cosmetics and penetration with a MIG torch. So in the top photo, you see TIG aluminum. To the right is MIG stainless, so I can do the same thing on aluminum as I can stainless with this. Also in this case, that could be a process, like a pulse process by the power supply, but we can also now control that from the robot too. So we can go between a pulse process and a CV process and control the frequency of pulsing back and forth between those two processes. And that's something, again, that's built into the robot using any power supply. More and more, though, again, the power supplies are getting smarter. You're seeing more and more servo torches being used, which are going to actually dip and retract that wire in and out of that weld puddle. So again, you can get a higher cosmetic, more controlled depth, and more controlled energy heat input on that weld. One of those, it's a nice video here by one of our partners, Fronius. They call it cold metal transfer. So I have a lower heat input, which is ideal when I'm welding materials like aluminum that have a very high heat dispersion rate. And let me pull the video up again. You'll see here what that retract looks like from that servo torch.
In CMT, the wire motions are fully integrated within the process. In addition, CMT Advanced also reverses the polarity in the short-circuiting phase. The arc remains stable, and the deposition rate is up to 60% higher. Combined with positively charged pulsing cycles, the process makes it possible to join super high-strength steels with complete process reliability. That's CMT Pulse Advanced. Another advantage, excellent gap bridgeability on light and ultralight gauge joints. Lower thermal input means less dilution of the base metal. This is a great advantage in weld cladding, with huge potential savings for users. With CMT, Fronius is doing pioneering work. Spatter-free welding, reliable steel to aluminium joints, crash test safe, making the impossible possible.
So again, heavy Fronius material there, but most of the power supply companies have a version of this now through different servo torches. They each kind of specialize in their own materials and markets as well. But I know SKS, Miller, Lincoln, they all have different versions of this, but kind of gives you that same idea of how those servo torches and pulse processors are working and providing new ways to weld things, even with just a MIG process. So lower cost than some of these others that we're going to look at. So also looking at aluminum thin metal, laser welding is becoming more and more popular as the cost comes down, but it's still a very expensive process. We'll typically have a customer ask us about laser welding and get a little bit of a sticker shock on it. But for some materials, especially in aerospace, it is the best process. So ROI is going to be much simpler in that case. Most popular with that is remote laser using a wobble head, and that's going to be inside a light type enclosure. So the robot's going to be doing some of that motion, but most of that weld motion and precision motion is actually occurring inside that laser head. So a little reflector prism aims that laser to the part, and there's, for example, built into the Yaskawa software, a way to calibrate that. So again, you have that extreme precision coming from the laser head and the combination of the robot. So you can kind of see here, you can do different weld seams, very narrow, small weld seams, even writing Yaskawa or serial numbers, whatnot, into place. So again, more and more popular for aluminum thin metal, as well as some other metal materials. Lately, we've also seen a gradual increase for laser seam steppers. So this is also using a laser. That laser head is inside of what they call a picker gun or a C gun, and it does not require a light tight enclosure. The laser head comes down to the part, and then on a C gun, the other side of the gun applies pressure, similar to what you'd see in resistance welding with a spot welding gun. But a picker gun actually is only one-sided. So the tooling is what's helping me apply pressure to the part. So if I have a large van floor, for example, I can get into the center of that part without having a large specialized gun. It's a very fast process, and there are no consumables in it, which is nice. So I don't have to dress my tips like I would in spot welding. But again, I have a higher rate of control with that. Also, more and more, especially in automotive, dissimilar metals being used. Variety of ways to tackle this. Again, we mentioned that in the MIG process. You could also do that with brazing. With silicon bronze, typically uses your filler metal. You could use the laser that we mentioned with that seam stepper. That'll work on certain types of mixed metals as well. Friction stud welding, which I'm actually spinning perhaps a steel stud onto aluminum or two different types of steel into place. One, though, that I wanted to touch on here that you see this large gun in the middle of the screen and the diagram on the right is flow drilling. So we hope to have a demo of this also at the trade shows this year. But I'm actually using a mechanical fastener. So the screw spins up very fast, the two different dissimilar metals. In that spinning actually creates the molten pool, so I get some flow there. And then as that pool cools, the fastener is fully inserted around that fastener. So the pool is actually creating a tighter joint than I would just screwing a fastener into place because of the rate of speed that it's being used at. So this being used, I've seen some applications actually on ladders, but in automotive engine cradles, battery trays, I know in some circumstances, but more and more this is being used. Again, you do have a consumable, you do have this screw fastener in place, but it's a little simpler and quite a bit lower cost than some of the other methods. And then lastly, for dissimilar metals is friction stir welding. And this is also kind of a newer process. We've worked with ESUB quite a bit on. I'm actually using a non-consumable sort of a router bit that plunges into the two dissimilar metals or similar metals, spins at a high rate of speed, applies pressure, travels along that weld seam, and joins those metals. I do have a video on demo of this as well to give you a better idea of how that works. But in this case, you'll see it plunge and just come straight toward the camera. Plunges into the two metals. The weld profile of this, if you do an etching, is almost like a spiral, like a cyclone between the two. So it's kind of a unique way of joining those metals as well. Back to the slide here. So lastly, I want to cover as far as with these advanced materials, different size parts that we're seeing, more and more mixed processes are being used. So I no longer necessarily have a cell for adhesive, a cell for spot welding. That's becoming more and more combined. So maybe I have to add spray foam for insulation on a car door panel, but I'm also going to be tacking and welding that in the same cell. So again, that happening more and more. I can also do inspection at the same time. All that's happening. So I'm eliminating some cycle time there. I'm eliminating different cells. I'm decreasing my overall footprint for the different machinery being used. So trying to combine all those processes into a single cell or a single line as possible is going to achieve a lot of efficiencies. Also with that, we're starting to see more and more, I'll touch on briefly here, laser ablation. So laser ablation, different uses. The military was doing a lot of R&D on this to actually remove the outer coating of airplanes so they could inspect airplanes. So it's using a laser that's basically just powerful enough, just hot enough, if you will, to burn that outer layer off. So that it burns it off instead of using a chemical process where you have a lot of chemical waste. So the only byproduct of this is basically carbon. And you can collect that carbon very easily and dispose of that much safer than you can that chemical waste. Where that's being used in automotive use, though, is say aluminum parts that might have some oil coating residue that need to be prepped for some other type of coating. So it might just be the paint outer surface. might be an adhesive, but that laser ablation process will clean that part and then present it directly to the next process. So you have a perfectly clean part ready to be applied with adhesive, paint, or even welded in that case. So that is all of our slides today. Again, a lot of information. I know a little time there in about 40 minutes. So I am going to look at the chat here, and our moderator has marked some questions that we'll try to tackle. And if I can't get to yours or I don't know the answer, we have all of this saved and we'll be able to answer offline. Also, if you are watching the rebroadcast of this or a recording later, you can present those questions. I believe there's a form on that page, and we'll also be able to tackle those questions at that time. So from Wayne Spooner, question is, how reliable is a sound signature in a real plant with all the ambient noise? That is a good question, Wayne. So typically that microphone equipment does have to be close to, obviously, the weld. So it could be mounted on end of arm. In our cells, it was actually mounted externally through sort of a shotgun microphone, which are highly directional. So that highly directional microphone is going to eliminate a lot of that excess noise. But not all of it. But when you're looking at sound signatures too, when it sees the frequency of that weld sound versus all the other sound, that's what it's going to pick up on. So there is some tuning that needs kind of to take place in a real world environment. But like the nature of everything artificial intelligence wise, the more you use it, the more you're training it, and the better it'll get. So it'll be able to filter out some of those other noises around you. Another question here from Lee Mulder. Can servo robot feed into cockpit? The general answer to that is yes. And I guess it's the what do you want it to feed into cockpit? So also at the trade shows this year, we'll be showing a servo robot inspection piece. So that inspection laser will scan a weld seam to determine, again, what the porosity is it within the right tolerances that we aimed it to be? And then that data, then as far as that pass fail or that measurement data, we can feed into cockpit, especially when it comes to the traceability records. I could also do that to possibly measure length of weld seam. So I know how much wire I've used today. I know what I've calculated the length of my weld seam should be on a given day or given part. But if I want to see how many meters of overall seams I did that day, I could export that data. So generally, yes, it just depends on what it is that you want to send to cockpit. Some of it's very straightforward. Some of it's just simple API layers that we have to create for those. Rohit Sharma asked as far as what are the limitation of laser cameras? Good question. I touched on just briefly as far as certain colors of lasers work better with molten metals. What I left out there too is that the reflectivity of the metal can cause some limitations. So some of the earlier lasers, red lasers that were doing scanning on a very shiny metal, say a highly polished aluminum or something that's been laser cut, that would cause too much reflectivity for the camera, and it couldn't get that right triangulation measurement. It was getting too much feedback, if you will. So that was some of the limitations to it. They have improved dramatically, though, with using the blue and green lasers. Again, some applications being simpler than others. You might require a little more fine tuning just depending on the type of that metal. So anything that's pooled on the metal, such as liquids, high reflectivity, high heat are just things that we have to work around, but we have been able to work around in the past. So overall, yes, there's limitations as far as the ease of use versus how much you're going to have to work around it. Sorry, we got lots of messages here, so I'm looking through ones that I have answers to today, some technical ones as well that I might not have an answer for you right away. Owen Captain ask, where can I get some more information on the Yaskawa cockpit? Good question. Although our offices, there's not very many people in the office, we do have a lot of information online, and almost all of our employees are working from home. So if you reach out to us on this or any of the applications you saw today, you can email me directly, joshua.leith@motoman.com. You should see on the screen now. I can direct you to the right person, or fill out the contact form on our website, and somebody will be able to get back to you on that. And again, I have some questions on, for example, CMT successful and zinc coated sheet. On the technical side, I'll have to check with Fronius on that. My gut is that it can be. So again, just depending on the application, thickness of material, what we have to kind of burn through in that sense. Again, I'm not a weld engineer. I am a product manager, but we'll be able to get you out the correct information on that. And I'm not seeing any other questions on the top here. So we will have this slideshow available for download. We'll have this overall presentation with my recorded message here also available for download. So be sure to share it if you think it's going to be valuable for somebody else. And again, I know it's high level information, but if there's something that sparks your interest there, please reach out. I'll get you some information, or somebody here will get some information. Also, on the zinc coated material, I just got a message from our weld engineer that's listening in that yes, galvanized is not an issue for CMT, and he has a lot of experience with that CMT. So thank you all again. I hope everybody stays safe and healthy, and please reach out to us if there's anything we can help out on automation, or answer any other further questions that you might have from today. And that's all. Take care.